So, good afternoon, everyone. Thank you for your introduction. My name is Antonio. I'm from the Polytechnic University of Valencia, and the work I'm about to present is about microcracking in cortical bone. This work has been made in collaboration with my colleagues Diego Infante, Ana Vercher, and Eugenio Jiménez. So, first of all, why are we studying microcracking in cortical bone? Well, today, degenerative diseases are becoming a major problem in society due to the aging of population. Understanding bone microfracture could help assessing the bone fracture risk. So, in order to study fracture, we would need some properties from the microconstituents, for instance, the strength or toughness, which are not widely shared in the literature. Because the literature about cortical bone usually centers about the morphometric analysis of cortical bone. And why? Because if we see here two different samples, one from a healthy bone and one from an osteoporotic bone, we can see some differences between them. For instance, the healthy bone is denser than the osteoporotic one. And also, if we observe the crack paths, we can see how cracks propagate through different microconstituents of bone. So, now that we know why are we doing this, let's start talking about bone structure. At the microstructure, we can differentiate two tissues for bone, spongy and compact or cortical bone. That's the one we are analyzing. Now, at the micromechanical level, we can see how cortical bone is composed of dense lamella of collagen that organize in a concentrical way around what we call a Hervesian canal. Inside the Hervesian canals, we can usually find blood vessels or nerves. The Hervesian canal, together with the lamella of collagen, form what we call an osteum, and that's the basic structural unit of cortical bone. Apart from osteum, we also can find the interstitial lamella or interstitial tissue, which fills the gaps between all the osteums in the microstructure. And taking a look at the cross-section of cortical bone, we can also distinguish another component, and that's the cement lines. The cement lines act as a weak interface through which cracks can propagate in order to avoid damaging the osteum and the blood vessel or nerves inside the Hervesian canal. Those cement lines also act as a toughening mechanism for cortical bone. And now that we know the microstructure and the problems with the simulation and research, we'll set two different objectives for this presentation. First, the characterization of fracture toughness and strength for the cement lines, which is not commonly found in the literature. For that, we are going to use a finite fracture mechanics approach. Once we've got those properties, we can go and try to simulate the crack path and propagation of the microstructure of cortical bone. To do so, we're going to use the cohesive model to model the failure of cement lines and the phase field model to model the failure of the interstitial bone. Because as we'll see later, during our experimental tests, the osteums didn't fail. So now, starting with the characterization of the cement lines, we first carry out some experimental tests. We prepare 4 samples of ovine cortical bone taken from the diaphysis of the tibia. We cut them in that beam-like shape. We clean the rest of the tissue apart from the cortical bone, and we notch them in the lower part. We can see that notch is here in that figure. Then carried out the mechanical testing, and we obtained 4 different curves for load displacement. Those curves will be used after to obtain the mechanical elastic properties of bone and the maximum load that they bear. Here we can also see a crack path starting at the cement line right at the notch that we created. I don't know if it can be clearly seen over there, but it's going over there and then jumps from an osteum to another through the interstitial bone. So now that we've got the experimental tests, let's go and explain the method that we are going to use to estimate the strength and toughness properties. We're going to use the couple criterion proposed by Leguillon in the framework of manufacturing mechanics. This criterion needs for the simultaneous fulfillment of both a stress criterion and an energy criterion along a characteristic length. As an example, we've got here this skin of a notch plate under tension and whose estimated characteristic length would be over here, right at the start of the crack propagation. Now, in order for the crack to propagate in that length, we need to fulfill a stress criterion, which is over here. In this case, in this figure, sorry, we can see the normalized stress plot as a curve, and we can see also an horizontal line which marks the beginning of failure. Over that line, the material or the point that we are analyzing has failed. And here on the horizontal axis, we cut the distance from the notch tip. Okay? So the stress criterion always provide an upper bound for an unknown that is the characteristic length. We don't know yet the value of that length in advance. And the other criterion we need to fulfill is the energy criterion, which provides a lower bound for that length. In this case, as you see here, the lower bound provided by the energy criterion is above the upper bound provided by the stress criterion. In this case, there is no failure in the structure. If we keep increasing the remote load applied, we could get to a point where both criteria match at the same point, providing us the characteristic length with this method. So now that we have an intuition about the method, what do we need to get? First, two curves, a stress curve and an energy release rate curve. We are going to obtain them through a numerical analysis. We created a 2D model of each of the samples tested. We used image segmentation near the crack propagation zone in order to obtain the osteons in gray and the interstitial bone in green. And far from the zone, the material was homogeneous. Here, we applied the load at which cracks started propagating during experimental testing in order to obtain the right point where crack propagation onset occurs. I want to emphasize that with this method, we are only going to use linear elastic analysis. We don't need to model any kind of damage yet. That will become later. And the 7 lines that I mentioned are just perfectly bonded here. So now, in order to obtain the stress curve, we just carried out the linear elastic analysis, applying the maximum peak load obtained during experimental testing. We obtained the stresses around the interface and rotated them so we could have a normal and shear component of stress, shown here. Here, the origin of this axis is right the point where the crack starts providing at the lower interface of our model. Once we got the stress curve, we go with the energy release rate curve. In this case, we needed to run several simulations, releasing a pair of nodes from the interface in each one of them. So we could have the strain energy calculated, and we could estimate a curve for the strain energy release rate depending on the crack length. I emphasize again, those are only linear elastic analysis. So once we've got both curves, we only need to estimate the strength and toughness. In order to do so, we set and define a factor mechanics based in best approach. In this approach, we use an objective function which contains a stress criterion here in red, in this case the quadratic fraction criterion, and an energy criterion. We want to minimize this function so that both the stress criterion and the energy criterion are equal to 1. Sadly, our experimental test had some variability, so we needed to set a tolerance in the restriction around the point that we already decided, which is 1. So, with everything set, we just need to run the optimization algorithm, and we obtain this curve that we had seen before for the simple case of a notch plate under tension for our cases. Here there are 2 different samples plotted. So the values obtained to plot this curve are shown in the table, and those are the values that we were looking from the beginning: strength and the toughness of the cement line. Now that we accomplished our first objective, we can go to the second one, which is the simulation of microcracking in cortical bone. So, in order to carry out this simulation, we will be using Abacus and specifically a cohesive interaction surface to model the failure of the cement line. Here, we selected the same criterion that we applied during the minimization problem, and we considered the same toughness for both mode 1 and mode 2 propagation. Here is a basic curve showing the bilinear behavior of our cohesive bond. And now, to model the failure of the interstitial bond, we use the phase field model. Here we are using the subroutines provided by Naviterani that uses the thermal analogy with phase field. And that's it. And phase field is based on the regularization of sharp cracks, converting them in a smear crack through the phase field variable. There's also another important parameter of phase field, which is the characteristic length L0 or length scale, which controls the width of the band in which the crack is diffused. So the properties for the interstitial bond were taken from the literature. And with everything, the properties that we calculated before for the cement lines and the new properties from the literature for the interstitial bond, we could run our simulation. Here we can see how the load is being applied from the upper side. And over here, we'll see how the interface starts fading, and then a quick propagation of crack goes upward. Here, the crack propagates from one failed interface to another in the form of a phase field crack, which is the variable that we are plotting here. So, another thing we did was to carry out a parametrical study of the length scale of phase field. What we saw was that the peak load was correctly predicted for both values that we tried, so there's no significant difference here in the peak load, but we see a sudden decrease in the force applied here. And so finally, we can compare both crack paths, the one from the numerical simulation and the one from the experimental test. We can see how the crack starts from the bottom and grows in a similar manner in both cases. And with all of that, we go now to conclusions. In conclusion, the first thing we did was getting an estimation of the strength and fracture and toughness properties of the cement lines using a finite fracture mechanics approach. The second thing we did was modeling the complex microcracking pattern using the cohesive zone model and the phase field model. And yet, I still need to mention some challenges that we are facing currently. The first one would be to develop a 3D model. The second one would be to obtain two different critical energy release rates for mode 1 and mode 2 on the same line. Of course, we could carry out a deeper characterization of other constituents, for instance, the interstitial bond, and trying some values and trying to estimate somehow its critical energy release rate. And finally, something that we are currently doing is increasing the number of tests that we carry out. Thank you for your attention, and thank you for being here.